fabricate them different ways, they use different tools. So the baseline is the same, yeah, the basic things that they use, but then they go way beyond that. They had to design and build and program these robots to pick up these tubes, so there's these different colored tubes, and they're different shapes, and if they put them in the right order, they get more points. The higher the tubes are posted up there, the higher the point score, and then if they get them in the right order, triangle, circle, square, then it doubles everything. And at the beginning of the match, they have these special yellow tubes. And at the first 15 seconds of the match, the robots are on their own. It's all the intelligence that's programmed in the robot to take that yellow tube, find the right peg, and hang it up there, all by themselves. And the kids take over and they have 2 minutes to do their thing and try to do the best they can. And it's also 3 teams together, so it's 3 on 3, and they come out here and they've never worked with these teams before, so they've got to figure out their strategy at the beginning too. What are you good at? What am I good at? Okay, this is what we're going to do. We really view this as the future of NASA, the future of our country, the contractors that work with us. We've got to have a talent pool to do the difficult things that are, on our plate, the challenges we're going to face. And so NASA's heavily involved in competitions like FIRST. This isn't the only one, but this is a good example. So we're involved on a lot of different levels. We provide some funding just to get teams started. Something like this was really kind of a university level design project. It takes some money. They're out there working with real materials, real machines, and so they have to pay for that. NASA provides mentors. So scientists and engineers and technicians that are working on NASA missions are also working with these kids in their high schools and in their communities to come up with the designs, to teach them what engineering is all about, and then to actually help them do the building, the machining, the programming, and the testing. So there's really a lot of different levels that we're involved with, just because it really is such a big part of what our future needs to be.
Second session of the NICE virtual PI meeting. Today we have our keynote speaker from NASA Langley, Dr. Bruce Wielicke. I'm going to give him a short introduction and let him take it away. Bruce has a PhD in physical oceanography from Scripps, and yesterday one of our presenters was also from Scripps, so there might be a little thing going on there. He did begin his career doing ocean and atmosphere dynamics, but he got into clouds in the 1970s when playing with an early climate model, and he's been working with cloud research ever since. He's published over 100 journal papers, served as project scientist on NASA field experiments. Was the principal investigator for the NASA Ceres, and currently serves as the science team lead for the NASA Clario mission. That's the Climate Absolute Radiance and Refractivity mission. And he's given lots and lots of lectures, including a lecture to our first PI meeting for the Global Climate Change Education Group back in 2009 or 10, I think that was. So with that,
all right,
I'll let you take
Thanks,
it away,
Lynn.
Bruce.
All right. Well, let's go ahead and start. I'm going to talk today about a particularly interesting topic to me, which is how do we take climate science and try to get people to better understand what the economic value to society is of climate science. So when we do that, I think one of the first things we have to do is talk about, for example, weather prediction. We think we have traceable estimates of economic value of weather prediction. For example, if we get more accurate hurricane tracks, or we get more accurate thunderstorm or flood warnings to people, we can save lives, we can save property. But for climate, we typically, as scientists, say, well, we're working on a problem that will affect societal decisions with trillion-dollar impacts in the future. But is that statement really verified or traceable in any way, or is it just a vague qualitative statement? How could we really quantify an economic value to climate science? Because it certainly is relevant to society and how they understand what we do as scientists. So one of the key differences of climate change versus weather is climate change science value really occurs decades into the future. As we learn better what's going to happen and do better predictions and make better societal decisions. And that value has to be treated almost as kind of a risk-benefit economic analysis because of its appearance in the future. There's both an investment perspective as well as a risk perspective, almost in the sense of an insurance. And rigorous analysis has to take into account uncertainties in both climate science, economic impacts, all together as a package, not just the science itself. We need to be sufficiently rigorous to basically get these kinds of things published in both economic and scientific journals. And then potentially, we hope something like this can change the dynamic of how we discuss climate change science in the public from just the threat discussions that you normally hear about to economic investment discussions. How do we actually better understand climate science to allow us to make better investments in how much we mitigate, how much we don't mitigate, how much we adapt, and what we can expect to happen in the future. So we need to start with what are climate observations. I mean, we already have an internationally agreed to set of weather observations to enable accurate weather prediction. Weather accuracy, however, is only about 1 Kelvin in terms of its need, whereas climate accuracy, we're typically talking a couple tenths of a Kelvin change per decade, so the accuracy needs to be 10 times more accurate, about a tenth of a Kelvin. Weather is basically variables of temperature, humidity, wind, and precipitation, whereas climate, you end up adding ocean currents, temperatures, salinity, including deep ocean, ice sheets, glaciers, sea ice, snow depth and coverage, atmospheric chemistry, including greenhouse gases and aerosols, as well as ecosystems for land, oceans, snow, and ice. So climate is basically 10 times the accuracy for 10 times the variables we have for weather prediction. So it's a lot bigger challenge. So we don't have an internationally agreed to climate observing system or monitoring system to improve climate prediction and understand what climate changes occur. And why not? Well, part of the reason I would argue is that it's really a communication, education problem between the climate scientists, the agencies that carry it out, Congress, and the public. So since necessity is the mother of invention, one thing you might think about is how do we kind of improve this situation? So one of the things I'm going to talk about today really came out of a bit of serendipity out of one of our missions called CLARIO, one of the NASA's decadal survey missions. And it stands for Climate Absolute Radiance and Refractivity Observatory. The mission goal is really to greatly increase by factors of 5 to 10 the absolute accuracy of our current spacecraft observations of Earth across a wide range of variables we measure in the system, or indeed across the entire infrared reflected solar spectrum and infrared emitted infrared spectrum. These are the spectrums we use to measure from space, temperature, humidity, clouds, radiation, aerosols, surface vegetation, snow, and ice sheets. So it's really critical to a lot of the variables we measure in climate change, and CLARIO's mission was to basically make that a much more accurate measurement. So how do we really do that? And to see that, I'm going to kind of shift to one of the slides so you can see it. This is just an example. CLARIO really is an example of taking kind of NIST advances over the last decade and launching them into orbit. So for example, what you would really see is a CLARIO satellite in the lower red orbit track there flying underneath one of our weather satellites like the NPP or JPSS satellites with weather instruments. And then matching as it crosses under them in time, space, and angle the radiances and actually allow a much more accurate calibration of those instruments than they can afford to carry into orbit themselves. So it leads to a very different design of instruments. A lot of the instrument is about its calibration system in orbit and not much about trying to map the whole Earth out. So you basically try for much smaller sensors with much tighter control over the accuracy of those sensors and use them to transfer that accuracy to other sensors. There's literally 30 to 40 such sensors in geostationary and low Earth orbits. Everything from the JPSS weather satellite system with the VIIRS imager, the CRIS interferometer for temperature, weather, humidity, a Ceres radiation budget. METOP is a European satellite system, weather satellite system. Landsat imagers for land processes, ocean color sensors for ocean phytoplankton, GOES imagers and sounders for geostationary, as well as chemistry. So really it's kind of a launching more accurate things into orbit, and as a part of that process in trying to understand how accurate we needed to be, the CLARIO mission team spent about a year trying to come up with criteria for how accurate you needed to be in orbit. And this slide kind of summarizes that for trends in temperature. So think of this as decadal trend uncertainty in temperature in degrees Kelvin per decade, 95% confidence. That's the y-axis here in the vertical. And the horizontal is length of the observed trend in years, anywhere from 0 to 50 years in this figure. And then if you look up here, you can see what the accuracy of the observing system is. And one of the key concepts we came up with was to metric the accuracy you need in climate observations with the accuracy of a perfect observing system. So a perfect observing system is shown here with calibration accuracy and orbit sampling errors of 0. And that, if I can find my cursor here, which I seem to have lost. That leads to the black curve in that figure where it's labeled as perfect obs. That shows that even with a perfect observing system in 10 years, off the glass. Oh, a perfect observing system, I think we've got operator error here. I've got it. In a perfect observing system in this black curve, in 10 years, you can only tell the accuracy of a decadal change curve to 0.3 per decade, because even with perfect observations, you still have natural variability, which is the noise in the climate system. Think of this as the nonlinear dynamic noise of ocean and atmosphere interacting with each other. And that noise will confound any signals you're trying to see of slow anthropogenic forcing of the climate system with things like greenhouse gases. So for example, our expected forcing for greenhouse gases is about 0.2 Kelvin per decade. And you can see in a 10-year record, the uncertainty due to natural variability with perfect observations is 0.3. So this is why when you see things in the media about a hiatus in warming of the planet for the last 10 years, that really doesn't mean much. It's still well within natural variability. When you really understand climate change, you need both accurate observations and you need a longer length of record. By the time you're at 20 years, you're down below 0.1 K, 30 years even smaller. But our current weather instruments are shown here, this EASI, AIRS, and CRIS at about 0.24 to 0.3 K for 95% confidence. And if I add those uncertainties and orbit sampling uncertainties to the perfect observing system, suddenly I get a less accurate observation of what's happening in the atmosphere. And now I have to wait longer by 15 to 20 years to get any given level of accuracy that I need for making decisions. So you can easily imagine if I'm looking for 0.2 Kelvin per decade trends, I want to be down here at the 0.1 or below. And now you can see I'm talking about needing 20-year records, and I'm talking about needing very high accuracy data. If not, I basically degrade it and move it out in time. So what does that look like? That's kind of the bottom line figure I showed you, but Lynn Chambers has done some analysis to give us a little different example of how this would work. So for example, one of our biggest uncertainties is climate sensitivity. How sensitive is the climate system for a given amount of carbon dioxide we put into it? So for high climate sensitivity shown in green, that means a 5% chance of occurrence, versus the most likely in red, versus in blue, the low climate sensitivity end. You can see there's a large range of how much warming we get by 2100. And I can tell you, as far as economic impacts, the amount of economic impacts we have basically scales with global average temperature. That's kind of like the volume dial in the climate system. And it's quadratically related. So if I double or triple the amount of warming, I increase the amount of economic impacts by a factor of 4 to 9. So that expected trend, this is what it shows if we had no natural variability and no observing system errors. This is what you would expect to see. However, that's not the real world we have. So now let's include natural variability, things like El Nino. And now you can see a lot more noise in the system of this high sensitivity, medium, and low sensitivity curve. Now if I take you one more step and I add our current observing system accuracy, you can now see how confused you can be in the first few decades of change between whether or not you're on the low, medium, or high sensitivity. And that, in fact, is where we have been for several decades in trying to understand climate change. If you look at how we could observe with higher climate accuracy by factors of 4 to 5 over what we currently have, now you can see those curves are limited again by natural variability, but now you can see much more quickly on the order of 20 years when you emerge from uncertainty and those things clearly separate themselves. So that's an idea of how you can get there. And here, if you put such an advanced observing system in place in 2020, you can see how you might take this noisier system and make it less noisy as you go out and observing climate change. So the other way we look at this to try to understand it more physically is in terms of climate sensitivity directly. Temperature, it turns out, is not a great variable by itself to try to understand climate sensitivity. Our biggest uncertainty in climate sensitivity is currently due to cloud feedback. This is, for example, low clouds in the climate system reflect back sunlight to space, but they don't really change the infrared blanketing of space. So basically, they can act as a cooling or warming depending on whether low clouds increase or decrease in the climate system as you go into the future as we warm the planet. So as we warm the planet, if low clouds decrease, which is what most climate models predict, you're going to let more sunlight reach the ground, less reflected back to space. That's going to add warming to the planet beyond the global warming you already put in to begin with. In that sense, it's a positive feedback. It's amplifying the warming the climate system is doing. So that's what we mean by climate sensitivity and feedbacks. And what you can see in this chart is the change per decade and change of the cloud's effect on the reflected solar radiation back to space, change in cloud rate of forcing in percent per decade. The climate models are shown here in green in the current IPCC report. And you can see the same behavior of a perfect observing system in black that we had for temperature versus our current observations, the most accurate we have of broadband radiation from Ceres, shown in gray. And then our imagers for things like cloud or surface properties are even less accurate. And now again, you can see this 15 to 20 year advance in understanding if you get more accurate data. So the idea would be, again, you launch Clario to calibrate Ceres and MODIS and VIIRS and CRIS and AIRS to do more accurate observations of the entire system. So if I can switch us back here, see if I can remember, there we go. So that kind of gave us a view on Clario of how accurate we needed to be. The basic answer that came back was we needed to be about a factor of 2 or 3 more accurate with our observations than natural variability. That meant that basically natural variability would dominate the uncertainty in climate change and not the accuracy of our actual observations. So a simple way to think of it is you determine the uncertainty by some of the largest sources of natural variability like El Nino. You make your accuracy requirement a factor of 2 or 3 below that, and that gives you the kind of results I just showed you before. So that leads to needing accuracies a factor of 5 to 10 beyond what we currently have in orbit. And one of the things we then did, and this is where the serendipity comes in, is none of us in science are economics people, but Roger Cook from Resources from the Future is from the economics community. He's a risk mathematician. He, it turns out, is one of the authors of the IPCC chapter on economic impacts in the future. He's been involved in that for some years. And he happened to be at NASA Langley about a year ago, and giving the aeronautics group here a discussion of how to understand their own economic value to society in terms of some of the risks they face, in terms of safety, for example. Well, the aeronautics group here knew we and Clario were doing some similar related things on climate, suggested Roger talk to us, which he did. And when we had given him the presentation I just showed you and walked you through, that was kind of the eureka moment for Roger. He knew the whole background of the economic models. So we then got together over the last year to do some studies on this. So basically what we did was try to merge the economic assessment models that come out of that community that Roger's associated with. Think of these as not climate models for the physical Earth, but instead models of the economic system, how the technology development evolves, how society evolves in terms of advancing the second and third world development, and how emissions evolve in terms of how rapidly we can try to change carbon emissions by going to newer technologies like renewable energies. So that really led to a merging of our Clario climate sensitivity uncertainty with what was going on in the economic assessment models. So if we look back at how that might be structured then, we then came up with this kind of logical structure for how to understand what's going on in the system. First, you start with an emission scenario, for example, business as usual, where the world kind of develops on the trajectory it's currently on. There are uncertainties of technological emissions innovation as well as global economic development. Then that emission scenario for things like carbon emissions or aerosols leads to an anthropogenic rate of forcing, how much we're changing the energy budget of the planet, which then changes its temperature. There's uncertainties there in things like aerosols and carbon cycle. Finally, climate sensitivity, this volume dial I talked about on the climate system, that now takes the forcing we have and converts it into temperature change. The temperature change then feeds other changes like water vapor precipitation, drought, sea level, melting of ice sheets, etc. So basically the climate sensitivity then leads to an amount of anthropogenic climate change. That leads to, in turn, future economic impacts once society sees both the scientific data of changes and forcing as well as the implied economic impacts. That's how society makes its policy changes, which then changes the emission scenario. So what we pretty much wanted to do then was to focus on here in the emission scenarios of these economic assessment models, and then something here, IMSCC, is the interagency memo on the social cost of carbon. This was an interagency study of about 12 agencies a few years ago, trying to agree on what's the actual cost to society of further emissions of carbon dioxide, how much it's going to cost, and everything from sea level rise to changes in agriculture to health. And that also had to include uncertainty, as we talked about before, in climate sensitivity, which we'll get back to in a minute. Then on our Clario side, we have been looking at uncertainty in climate sensitivity and how to reduce it, basically by getting more accurate observations over a period of time until we could reach the limit of natural variability. And then again, future economic impacts, these economic impact assessment models can deal with. So basically, that's the version of this loop. We are trying to set up a structure to understand the framework of how you might try to understand the economic value of narrowing uncertainty and climate sensitivity in assessing the economic impacts into the future. So this is just a simple schematic of what was involved then. We had our Clario climate accuracy framework I told you about first, this social cost of carbon memo from the interagency report to use. And then one of these, we picked one of the three main integrated climate economic assessment models called DICE. And then that gave us a way to try to address this global value of the economic value of science. And the key here, again, was this IPCC uncertainty of a factor of 3 or 4 in climate sensitivity. If you want to know 90% confidence bounds, it's a factor of 4. And a factor of 4 uncertainty in climate sensitivity is a factor of 16 uncertainty in economic impacts. So what does this look like schematically then? If we take a discount rate of 3%, and I'm going to need to do a little sidebar here, because most people aren't familiar with what discount rate is. We all know about inflation, how things will be inflated in terms of value in the future. This is very different than that. After you've accounted for inflation, discount rate means every individual is less interested in things they'll have in the future than they are interested now. And that discount rate tries to account for what's that drop of value of things into the future relative to today. And the discount rate of 3% we've used as the nominal is the thing that came out of that social cost of carbon memo. And they had a range of 2.5% to 5%. And I'll show you later some of the results of all three of those scenarios so you can understand how important that is. But you can also see that at 3% a year, if I go out 100 years, that's going to reduce by factors of even 3 any economic impacts that are out past 100 years. So it pretty much tends to downplay the far out economic impacts and focus more on medium-term to short-term economic impacts. And this schematic shows for business as usual emissions, if you go into that social cost of carbon memo and integrate up the costs with this discount rate of 3% and to reduce them, you'll then still get a social cost of carbon of about 209 trillion through 2205. Most of those impacts are back here in the sort of next 3 to 7 or 8 decades. And our current observations, where we're still struggling with the accuracy with which we know and how we can predict future climate change, we have arguments going on of when will we really know with high confidence how much climate change we're going to get. And given this factor of 4 uncertainty in climate sensitivity leading to a factor of 16 in economic impacts, that's a challenge for society to deal with. If we wait to change our emissions strategy to 2055, as shown in here, you're then going to reduce this 209 trillion social cost of carbon down to 65. That's a big help. So that's what you might expect with our current observing system if we go on arguing for decades about how much we know or don't know about climate change. If you take a 20-year advance in that, as I was talking about in those earlier charts with more accurate observations, you can now see that that economic impact gets reduced to 53 trillion. So the difference between 65 and 53, or 11.7 trillion, is basically the net present value, including this discount rate, of advancing by 20 years a decision to a lower emissions path for climate change. Now, the other thing you have to do is come up with a decision context to decide how this would actually be done. And so this gives you an idea of the context we've looked at. Changes in temperature per decade is one context, or changes in this shortwave cloud rate of forcing, the reflectance of clouds back to space per decade. This one in clouds relates more directly to climate sensitivity. The one in temperature per decade relates less directly to climate sensitivity. So we've looked at different thresholds on climate change per decade, different statistical confidence levels, different dates you might launch an advanced climate observing system. And this is not only Clario, but Clario is being used as an example here. This would really be a full climate observing system, which we don't currently have. And then different discount rates, 2.5%, 3%, or 5%. And finally, if you're going to put temperature thresholds, you really need to understand aerosol forcing as well to understand how much total forcing. That isn't so critical for cloud-rated feedback, but it is for temperature changes. So we assume that improved aerosol observations will be put up as part of this improved climate observing system as well. So we then took a whole distribution of climate sensitivity, this 90% confidence bound from the IPCC, from 1.7 degrees C warming for doubled CO2 equilibrium response at the low end to 7.1 degrees C for doubled CO2 equilibrium response at the high end. And those were put into this social cost of carbon mapping of temperature change per decade over the next century. And then we added as well a full PDF of climate sensitivity, a full PDF of climate natural variability, and literally ran thousands of Monte Carlo simulations of what different economic impacts and different abilities to detect climate change with these different triggers and confidence bounds you would have. So that really led us to the next table, which is kind of a summary of those results. For the nominal 3% discount rate, the baseline case I talked about, this is with 0.2 degrees C per decade warming trigger, leads to 11.7 trillion value for moving forward in time. If you change the business as usual, instead of a moderate emissions scenario, you go to an aggressive emissions scenario. This is more like the Stern report from 2007, changes to about 9.8 trillion. If you increase the trigger from 0.2 degrees C per decade to 0.3, value increases to 14.4. If you do a 2030 launch instead of 2020 launch, 10 years later, of an advanced climate observing system, you drop the value from this 11.7 to 9.1. So you lose $2.6 trillion in potential benefit for a 10-year delay. So you can think of that as the cost of a potential delay per year of advanced observations is on the order of 260 billion. So these are large numbers. They were surprisingly large to us, but they come out of this social cost of carbon analysis. We can also look at varying discount rate. Here's 2.5%, 3 or 5%. You can see how dramatically that varies the value. The more we discount future value, the more it reduces the value, economic value, the less we put it in. And the economics community is still arguing about what these values ought to be, so consider this kind of an uncertainty factor. We can also look at what would be the cost of 30 years of improved full climate observing system data. And our estimate there, we're just using a rough ballpark of roughly quadrupling the current effort, which is about 2 to 3 billion per year in the US and about the same in the international community. That would add up to, in terms of net present value, about 245 billion over 30 years of data. If you ratio these two, you'd get a payback factor of about $45 for every dollar invested in advanced climate observations. So to summarize what we've done so far, and this is just an initial framework we've developed, we've looked at what an advanced climate observing system could do to accelerate, and let me change my view here for you. What an advanced climate observing system could do to accelerate accurate societal decisions by 15 to 20 years over current systems. One of the key advances is higher absolute accuracy in decadal change observations to reduce uncertainty in key areas like climate sensitivity. The net present value to the world economy of such an acceleration is on the order of $10 trillion in terms of 2015 US dollars. The net present value of an advanced climate observing system is relatively robust to changing decision trigger or emissions reduction approach. And as an investment, you could literally look at order $45 for every dollar invested. And every year we delay could drop 260 billion. So next steps are to look at the current study using climate trend decision triggers. We've submitted the original paper to Environment, Systems, and Decisions. The current study doesn't include the emissions costs of mitigation, so those will have to be added in the next version of this simple study. That might reduce the value of information by a factor of 2 to 4. The next version will also include analysis triggers for cloud feedback, which will give us a more direct relationship to climate sensitivity. And then we'll probably try to address this framework and extend it to other things like uncertainty in aerosol forcing, carbon cycle, or sea level rise. If you wanted to change this to the US, as opposed to world economic value, you drop that by a factor of 6, but then the US cost of climate observations would be only half of what I had in those earlier analyses. If we do both the mitigation reduction and the US, you might be looking at the US getting back something in the order of $5 per dollar invested. And that's where we'll stop and ask for any questions. Okay. No. Okay.
I was just hoping you could explain a little bit more about, I didn't quite understand the discount rate
Okay.
and how those three values you explored sort of relate to what economists expect it to be.
Okay. All right, so we've got one question on what discount rates are, and that's not something as scientists we normally deal with. First off, you need to know discount rate is not inflation. It doesn't have anything to do with inflation. It really kind of accounts for how people value financial resources as a function of their perceived utility, both now and in the future. So you've heard the phrase, a bird in the hand is worth two in the bush. That's an example of discount rate. Another example is future generations will be richer than us as the economy of everybody evolves. So some people would say, well, let's let them deal with the costs. Investments made today have to be compared to alternative ways to invest the same resources. So again, a discount rate tries to understand that kind of the whole combination of those different effects on how people value money they might spend today on a climate observing system versus money they might get back several decades in the future by a better ability to not over or under mitigate climate change. Good question.
I have a question.
Sure.
What are the pathways to get some of this presented to our legislators so that we can act on it?
Good question. So the question is, what's the pathways we can kind of get some of this information out to people who could act on it? We've certainly been presenting this information to people like NASA headquarters and even some of our local congressional staff, just so they can have a better understanding of where this might go. We've, as I said, submitted this to a journal because I think this sort of thing shouldn't be taken really seriously until it's been through journal peer review. We want to get some of the next step studies done as well. And then we'll do this in both economic journals and scientific journals, make sure it can stand the peer review of both. Then I think we'll have a more serious product that could really get into the national and international discussion of how do we get ourselves to an international global climate observing system that we currently lack. Good question. Mm-hmm. Okay. You want me to put us back on?
Yeah.
Okay. See if I can do that. I can remember which way we're going. I keep forgetting which button.
Okay.
There we go.
So while we're waiting, we've just put back up on the webcast the email to ask questions. So if you just saw that, you can send in your questions. But while we're waiting, I just thought I'd pop in here and remind everybody about tomorrow's session, which will be at 2 p.m. Eastern on both the reporting, and we'll have updates for FY13 reporting, and on the the Earth Science Education product review process. And then Friday at 1 p.m. Eastern, we will have the session on the 508 compliance. So again, if anyone out there has some documents that you're having trouble getting to be 508 compliant, please send them to me so that we can send them to our presenter in advance so that he can take a look at them and hopefully do some real-time 508 compliance help on Friday.
Okay.
So it looks like we have a question. I'll pop back
All
out.
right. Okay.
I'll just ask
preserving technology could lead to more accuracy in climate prediction?
Actually, very sure, because one of the things we've done in the climate community is to learn how to actually take climate models, for example, that are their own planets. They're not the Earth, but they're a different climate system that's like the Earth, and learn how to take the data that comes out of those, that could be observations if you want to think of that, and then understand how to unscramble cloud feedbacks and climate sensitivity in those models. So we've been able to separate out water vapor feedback, cloud feedback, temperature lapse rate feedback, snow and ice albedo feedback, and get what the sensitivity of those models is. But one of the things we've found in doing that is you need decades of data to do that. To do it from just comparing climate models to current mean climatologies doesn't give you that kind of uncertainty in how well climate models are doing climate prediction. So certainly there will still be uncertainties. Just more accurate data by itself isn't enough. We still need the process missions to study the individual processes we don't understand well enough yet. But even narrowing the uncertainty of what the real climate system's climate sensitivity is will be a big step in that direction to help us more accurately know where we're going. But that certainly doesn't mean I'm trying at all to discount the fact that, for example, ice sheets and sea level are still a big question about how rapidly the ice sheets can lose ice, how rapidly sea level can rise, and even how rapidly the carbon cycle might change in terms of uptake of carbon, and even in terms in the Arctic of as permafrost melts, will you actually get large releases of methane and carbon dioxide into the atmosphere, which is itself a potential positive feedback in the climate system. So it won't answer all questions, but I think it's a big step in the right direction, and I can tell you if we don't have accurate observations, we will mull around in a mess for a really long time.
So there's another question. If you could repeat it so everyone on the air can hear it.
Sure.
It's where can I go to learn more about how economic impact of climate change is estimated?
Can you repeat that again?
Where can I go to learn more about how economic impact of climate change is estimated?
Very good question. So the question is, where do I go to learn more about how economic impacts of climate change are estimated? There's two places I would send you. One is you can go to the IPCC report itself. There's a whole 1,000-page document on economic impacts, but there's a policymaker summary that's 20 pages. You can get a quicker sense. And then the other thing is this interagency social cost of carbon memo in 2010. If you Google interagency social cost of carbon memo in 2010, you will get that. And that report will tell you about how they've done that study as well. Good question.
Scientists and educators may be really aware of climate science, but mystified by economics. Can you share what it was like to work in that sphere?
Very good question. So the question is, the public and Congress has been hearing about climate science, and some of them may be a bit mystified about economics. What was it like as a scientist to go into the economic sphere? And I can tell you it was fascinating, actually. I mean, I had a lot of help from Roger Cook in what are some of the key books to read. A good example was this DICE model by Nordstrom. He has a book that he's written on how he put that model together. It's a publicly available model in a spreadsheet. You can go look at that. That interagency social cost of carbon was good. And I found it fascinating to get into a very different realm than our normal scientific realm. And I think if any of you want a fascinating book to read on how economics has even evolved over time, a recent one is the one on thinking fast and slow. How we make decisions, which isn't always actually in our best interest. I highly recommend that book to people as well. But there's certainly some good ones. If you want to, Lynn can certainly get information to me. If any of you would like some recommendation of sources to read, that are very readable. I can certainly pass the ones on to you that Roger did for me, and it helped a lot. We actually had a lot of fun doing those discussions. It was fascinating to both be teaching him climate science at the same time he was teaching me economics. And we certainly look forward to hopefully continuing this kind of study and using it to really set up an architecture that other people can build off of in the future. That's really what the hope of our vision was in this kind of study.
So, follow-on question on that. A lot of the people in the audience might be professors, so
Mm-hmm.
if their students are science or education students, would you recommend to them that they take the economics class?
So the question is, since many of you out there are in the education community in college, would you recommend that students take an economics class? I think it certainly would help if you're trying to understand the bigger picture dynamic of how the world works. There's no question that economics is a major player in what all of us do. It also can be useful to you in your personal life. So yes, I think I certainly would recommend that. You should realize in just a first economics class, you won't get necessarily all the most advanced stuff. You're not going to hear probably economic discussions of climate change in there, but you certainly could learn the basic principles, and certainly things like discount rate I talked about would be in there for sure. Okay. All right. Well, thanks for listening to us, and hope you found today interesting. And don't be shy about sending any further questions by email or asking for any guidance.
Science begins with questions, and your students have many. Our Magnificent Sun is an interactive program specially designed for students in kindergarten to second grade. With the help of a NASA Digital Learning Network education specialist, students will have fun learning about the sun's motion, color, and features, and then discuss how the sun and the earth are connected. No need to worry about collecting materials for your class. NASA's Digital Learning Network takes care of the prep work needed. For more information or to register your class, go to dln.nasa.gov. Come along and learn about the sun with NASA.
Hello, I'm Leland Melvin, NASA Associate Administrator for Education and a two-time Space Shuttle astronaut. A new era of space exploration is upon us. NASA is building the next generation of space vehicles that will help us explore the unknown and push the boundaries of human exploration. But there are challenges along the way, and NASA needs your help to solve them. The NASA Exploration Design Challenge is an opportunity for you to come along on the journey to deep space by tackling one of the toughest challenges of long-duration human space exploration: radiation. How will we protect our astronauts from the dangers associated with radiation as they venture to places humans have never been before? What new materials will we need to safely explore these undiscovered worlds? Students from kindergarten to 12th grade can participate in NASA's Exploration Design Challenge, learning about and helping to solve the challenge of radiation in deep space travel. And for your efforts, your name can actually be flown on the historic flight test of NASA's exploration vehicle, Orion. Serving as a virtual crew member on this flight, you can take your place as part of the Orion team, joining people from NASA and Lockheed Martin as they launch us into the future of space exploration. You are the engineers and scientists of tomorrow, And by participating in challenges like the NASA Exploration Design Challenge, you'll be cultivating the skills and knowledge to develop our future in space and here on Earth. Join students from across our country and around the world as you chart your exploration pathway. I hope you will get involved in the NASA Exploration Design Challenge today.
NASA Johnson style. Johnson style. Welcome to NASA's Johnson Space Center. We are coming in hot, so don't burn up as we enter. We do science every day that affects your daily life. Throw them up for manned space flight. Science everywhere as we engineer the marbles that fly through the air and take us way beyond Earth's level. Science everywhere because we engineer the marbles that fly through the air, flies us through the air. Control the mission out of Johnson. This is ground and this is space. Tell me, Houston, what's the problem? It's okay, oh it's okay, because there's flight controllers on the job today. NASA Johnson style. Johnson style. NASA Johnson style. Johnson style. NASA Johnson style. Hey, science daily. NASA Johnson style. Hey, it's amazing. NASA Johnson style. Orbiting Earth International Space Station, where we work and live in space with a crew from several nations. Got Japanese and Russians and that European charm. Throw 'em up like the Canada arm. Kicking out research. 29K cubic feet revolves around the Earth. Science microgravity revolves around the Earth. Columbus jamming destiny. Kicking out research. Kicking out research. Train the Astro, NASA Johnson, to go to space, to go to space, cause the missions of tomorrow start today, they start today, as we engineer the future day by day. NASA Johnson style. Johnson style. NASA Johnson style. Johnson style. NASA Johnson style. Hey, science daily. NASA Johnson style. Hey, it's amazing. NASA Johnson style. Ryan Moore, SLS and PCV, we cannot feel the floor. Cause the lack of gravity, the destinations are an asteroid, Mars, or the moon. We are blasting off, start the countdown soon. Ignition sequence start. 6, 5, 4, 3, 2, 1. Hey, science daily. NASA Johnson style. Hey, it's amazing. NASA Johnson style.
Indoor, definitely, because it's the forest planet. It would be a nice habitat. Maybe Tatooine, because then you can have like a beach, resort out there. You could probably do that. I'd probably stay away from Mustafar, because, when people go to Mustafar, they end up losing limbs and getting